Row 1. Text, Notepad window, text editor, editing, Microsoft Candidate UI, pane, blank. Remember, this is not teaching man teacher. It is useful for recalling when exam coming man student. Just close eyes and listen. Based on G scheme for Electronics Engineering Group. Subject, Advanced Communication System, 17656. These are mostly important questions which is always repeat, form top. To end it, reduce repeated changes. X question 1 is more important than 2 in notes. And note warning sign that this is not all chapter. Download link is below.
One. Advanced Communication System Chapter 6. Answer 1. State splicing techniques used for optical fiber. Explain any one in detail. ANS, State 1M, Diagram 2M, Explanation 1M. Different types of splicing are 1. Fusion splicing, or welding 2. Mechanical splicing 3. Elastic tube splicing. Fusion splicing. It is accomplished by applying localized heating I.E. by a flame, or an electrical arc, at an interference between two budded, pre-aligned fiber ends. The figure shown below. Fig. Fusion splicing. This technique involves heating of two prepared fiber ends to their fusing point, by applying sufficient axial pressure between the two optical fibers. For heating, most widely source is electric arc. Following are steps for fusion process. Prefusion. It is a technique which involves the rounding of the fiber ends with a low energy discharge before pressing the fibers together. By moving movable block, with proper pressure, two fibers are pressed together, then there will be accomplishment of splice. 2. Advanced Communication System Chapter 6. Answer, or mechanical splicing, using rigid alignment tube. In this method, accurately produced rigid alignment tube is used to bond the prepared fiber ends permanently. Figure shows the snug tube splicing. In snug tube splicing technique uses a glass or ceramic capillary tube with an inner diameter just large enough to accept the optical fibers. Transparent adhesive is injected through a transverse bore in capillary to give mechanical sealing and index matching of the splice. Average insertion losses as low as 0.1 dB have been obtained. Figure shows the loose tube splice. In this splice, an oversized square section metal is used to accept the prepared fiber ends. Transparent adhesives are first inserted into the tube, followed by the fibers. The splice is self-aligned when fibers are curved in a same plane. Mean splice insertion losses of 0.73 dB have been achieved. Or using V-grooves. Fig. Mechanical splicing. 3. Advanced Communication System Chapter 6. Answer. In this technique, V-grooves are used to secure the fibers to be joined. This method utilizes a V-groove into which the two prepared fiber ends are pressed. The V-groove splice ends through insertion in the groove. The splice is made permanent by securing the fibers in the V-grooves with epoxy resin. For single-mode fiber splice, insertion losses of less than 0.01 dB. Or elastic tube splice. 1. The elastic tube splice, shown cross-sectionally in the figure below, is a unique device that automatically performs lateral, longitudinal, and angular alignment. 2. It splices multimode fibers with losses in the same range as commercial fusion splices, but much less equipment and skill are needed. 3. The splice mechanism is basically a tube made of elastic material. The central hole diameter is slightly smaller than that of the fiber to be spliced, and is tapered on each end for easy fiber insertion. 4. When the fiber is inserted, it expands the hole diameter so that the elastic material exerts a symmetrical force on the fiber. 5. This symmetry feature allows an accurate and automatic alignment of the axes of the two joined fibers. 6. A wide range of diameters can be inserted into the elastic tube. Thus the fibers to be spliced do not have to be equal in diameter, since each fiber moves into position independently. Relative to the tube axis. Fig. V grooves. 4. Advanced Communication System Chapter 6. Answer. 2. Compare LED and laser. 8 points. ANS. Comparison Senior No. LED laser 1 low efficiency high efficiency 2 response time is slow response time is fast. 3 lower data transmission rate. Higher data transmission rate. For used for lower transmission distances. Used for greater transmission distances. 5 dispersion is less. Dispersion is more. 6 less temperature sensitive. More temperature sensitive. 7 lower bit rate. Higher bit rate. 8 lifetime is more. Lifetime is less. 9 broad output spectrum. Narrow output spectrum. 10 provide more distortion at output. Provide less distortion at output. 3. Draw structure of avalanche photodiode and describe its working principle. ANS, 2M diagram and 2M explanation. Or schematic of an elastic tube splice. 5. Advanced Communication System Chapter 6. Answer. Avalanche photodiode is a major type of optical communication detector. The structure of it such that to create an extremely high electric field region. The depletion region where most of the photons are absorbed, and the primary carrier pair generated there is a high field region, in which holes and electrons can acquire sufficient energy to excite new electron-hole pairs, i.e., process of impact ionization that leads to avalanche breakdown. It requires high reverse bias voltage in order that the new carriers created by impact ionization can produce additional carriers by same mechanism. 4. Draw block diagram of Otdr and explain its working. An optical time domain reflectometer, Otdr, is a versatile portable instrument that is used widely to evaluate the characteristics of an installed optical fiber link. In addition to identifying and locating faults or anomalies within a link, this instrument measures parameters such as fiber attenuation, length, optical connector, and splice losses and light reflectance levels. An Otdr is fundamentally optical radar. As shown in Fig, the Otdr operates by periodically launching narrow laser pulses into one end of fiber under test by using either a directional coupler or a circulator. The properties of the optical fiber link then are determined by analyzing the amplitude and temporal characteristics of the waveform of the reflected and backscattered light. A typical Otdr consists of a light source and receiver, data acquisition and processing modules, an information storage unit for retaining data either in the internal memory or on an external disk, and display. Figure shows a portable Otdr for making measurements in the field.